and its electric field. If there is a set of infinite number of charges in a space, how can you calculate the electric field by it? How can you calculate the electric field by a point, at a point, if there is a set of infinite number of charges? This is our point of discussion. The principle of superposition, as we know, that is applicable for a finite number of charges. A core system of multiple charges, countable number of charges, where the electric field, the net electric field, is a vector sum of all the charges. There is a countable number of charges. But if there is an infinite number of charges, we cannot add up, or we cannot take the vector sum of all the infinite number of charges. It is not possible mathematically. There, it finds the application of another mathematical concept, that is calculus, differential calculus and integral calculus. Differential calculus uses differential functions. These functions uses infinitesimal values. Infinitesimal values. The value is so small that is beyond our imagination. That small is the value we take it in that differential calculus. We estimate using differential calculus for infinitesimal value. Then for the total value, for a net value, we integrate the differential equation. The total value, it requires integration of the differential equation. That is a mathematical technique we apply for a total effect by infinite number of charges. Let us go for this idea. Let us go for derivation of the electric field for that kind of that set of infinite number of charges. Before we shall go for it, let us understand the meaning of the term. It is important to understand the meaning of the term continuous charge distribution. Continuous charge distribution. What is meant by the continuous charge distribution? If an object acquires charges across infinite number of charges it acquires. The charges may be positive charges or negative charges. But after the acquisition, we see that what will be the distribution of the charges? The charges, of course, they are distributed on the surface of the material, surface of the object, distribution. What would be the type of distribution, or what kind of distribution we observe? The distribution is either a continuous or discontinuous. The distribution is either continuous or discontinuous. Discontinuous is discrete. What is meant by discrete? Discrete means there is no uniformity in the distribution. Charges are not uniformly distributed at the surface. That is called as discrete. What is meant by continuous distribution? It is a uniform distribution. There you see That is a pattern of uniform distribution of charges. What is meant by uniform distribution? It is all the charges, that is all the charges on the surface are bounded by or bound together, bound with each other. All the charges are closely associated with each other with no space or little space in between them. That kind of distribution is called as continuous distribution. The charge distribution is continuous only when the charges are closely packed on the surface. It is called as continuous charge distribution. There are three types. It is linear charge distribution, surface charge distribution, and volume charge distribution. So in this continuous charge distribution we have three types. This is the one, second one, and third one. The reason for this, the distribution depends on the shape of the object. Distribution depends on the shape of the object. As you know, the shape of objects have three possibilities. That is one dimension, two dimensions, and three dimensions, spatial dimensions. The object can have three different types of spatial dimensions. One dimension means it is linear charge. One dimension means a line or one dimension. It looks like a line. It is like a thin wire. A single line, straight line like this. A linear charge distribution. Or it looks like, what is that? Two dimension is, that is a plane like this. That is a plate like this. Dimension, two dimension design. So it is, the charges are distributed in the plane like this. It is called as surface charge distribution. The charges are distributed in three dimensions. Any shape like this in three dimensions, it is called as volume charge distribution. So it depends on the shape of the object on which the charges are getting distributed. Maybe of linear shape, or what is that, two-dimensional shape, or three-dimensional shape like this. So in this, what is that continuous charge distribution, these are the three possible kind of, or three possible types we expect. This continuous charge distribution is characterized by the term. It is an important term. It is characterized by, that is, charge density or density of a charge on the surface. The density of charges. It is also called a charge density. What is meant by the charge density? Charge means here the charges are distributed, charges are distributed. The total number of charges distributed in that region, that divided by the area, or what is that? The region. What is that? The region or the area. It is either in the form, what is it by? In the form of length or area like this or volume like this. The total number of charges distributed divided by the area they occupied. Maybe a length in case of one dimension, or area, surface area in case of that two dimension, or volume in case of three dimension. That is the occupation of the, what is that? Spatial dimension. The spatial dimension is linear, therefore length. In this length, how many charges present? There is a total number of charges and divided by the length. In this area, how many charges are present? Total number of charges divided by the total surface area. And this Q by V, it is how many charges are present in this volume. In this volume is the V. It is called as charge density rho. It is volume charge density. This is surface charge density. This is linear charge density. This charge density characterizes the continuous charge distribution. This charge density, it remains same. The charge density will remain same when you observe at every point on the line, at every point on the space, at every point in this volume. If that is the case, that charge distribution is called as continuous charge distribution. What is continuous charge distribution? It is characterized by this charge density. It is a ratio of this amount of charge divided by the area where it is, what is the space where it is occupied. So this will remain same at every point in this dimension, at every point in this dimension, at every point in this dimension. It is known as continuous charge distribution. It is more appropriate to explain the continuous charge distribution. So this is what the distribution, and we can write this is in the form of differential equation. That is a differential form. Q divided by L, the total charge divided by total length. What is the differential form of this? dq by dl. dq is infinitesimal amount of charge. That is very small, infinitesimally small amount of charge. Present in which length? Only infinitesimal length dl. So this dl. So this amount is present in this length. Infinitesimal charge, infinitesimal length. That is by differential form. So if that is the case, we can rewrite this equation as dq in the form of, what is that? That is cross multiply. We get dq is equal to lambda into dl. That is the linear charge density equation for this one dimension. This is for two dimension. This is for three dimensions. Now the question is, we have to find out what is the electric field at a point due to this set of charges. At this point, due to this set of charges. At this point, due to this set of points. Generalized form. Yes, I want to write it. So recall the standard form for electric field at a point. So this is electric field, but if I change, of course, this is electric field at a point is equal to, it is known as Coulomb's constant into the amount of charge which is at a distance of r from the point. Amount of charge, it is at a distance of r from the point. That is electric field at this point. That is a standard formula. It is a known definition for electric field, mathematical definition. We shall write this for what is that? Infinitesimal change. That is, if q is equal to dq, I am taking this element, not entire thing. That is the element, infinitesimal element. This is a dq. What is the electric field by this element at this point? It is d. We write this. If this is dq, this is d. For infinitesimal value, we have infinitesimal electric field at this point. So rewrite the same equation, definition for this point. K remains Coulomb's constant is always the distance of separation. So what is the distance of separation of this charge from this point? That is the differential form. Differential form, I said, it is for infinitesimal change, infinitesimal value. But here, infinite number of charges are there. I want what is the electric field for the entire charge, entire amount of charge. That we get it for the integration of the equation. That is integration of this differential equation. This is a differential equation. Integration of the differential equation, integration of the, that is left hand side, this is right hand side. Integration of left hand side is E, that is finite value rate. Integration of right hand side, that is K lambda is constant, take it out. Integration of the variables dl by r square, that is integral. Now this right hand side should be integrated with respect to spatial dimension of the region. That is integration with respect to spatial dimension of the region. The region is one dimension, here two dimension, this is three dimension. For integration with respect to this one dimension, that is dl, two dimension dl, ds, three dimension, that is still under dv. So this is a general form of what is the integration. This requires, what is that integration requires, it is correct limitation, integral limits, lower limit and upper limit. This always take lower limits of integration. For this integration require correct limits of integration. For this integration, this is generalized form I have written. So now it is clear about now distribution of charges, the shapes like this, linear shape, planar shape and voluminous shape. And the electric field general formula is this, that is general formula is it is uses what is that equation of what is that charge density, equation of charge density, equation of the charge density. Upon integration we get the finite value, that is the total value of this field. With this knowledge, let us go for derivation for the electric field at a point. Derivation for electric field at a point due to this linear charge distribution. Derivation for electric field at a point due to linear charge distribution. This diagram written, this is the same thing I written here. This is a linear charge distribution diagram showing linear charge distribution. Charges may be plus or minus, I am taking plus charges. Arrangement is only in a linear fashion. The same thing I have taken here in this fashion. Here is a linear direction, is vertical direction like this. We are going to find out the potential electric field at this point here, and at this point it is placed like this with respect to this. This is placed like this with respect to this. That is axial, along the axis of the linear charge. Here along the vertical line drawn to linear charge. This is vertical line drawn to this point. This point. Now we go for mathematical derivation. That is an important one. So this will take what is that a mathematical procedure. Of course, a different kind of mathematical methods we are using. So let us go for derivation for the electric field at this point. It requires this geometrical drawings, linear charge. So here q number of charges are distributed here in linear shape, that is q. Let the length of the charge is L, that is the length of the charge, length is taken as dx, infinitesimal length. This infinitesimal length occupies infinitesimal amount of charge dq. So this is a point where this charge can act at this point, produces electric field, that is infinitesimal electric field dE. And the distance of this charge from the point is x, let us call this as x. And also distance of this point from this end of the charge is a. And the distance of the point from this end of the linear charge is L plus A. This kind of what is a geometrical drawing is required for this mathematical derivation. I have taken the point here. This is a linear charge of length L. The distance between this point and this end is A. The distance between this point and this point is L plus A. And the distance between this point and this point where the charge amount is dq is x. And the distance occupied is dx, infinitesimal length. This is the one. And total charge is 2. But we are taking only dq charge. Let us calculate the electric field only by this amount, infinitesimal amount. Write the equation. Write the equation. The same equation. dE is equal to this one. d is equal to this is one I have written. Here distance separation is r I have taken. Here distance separation is x. That is the only difference. And replace dq by equation of linear charge density. That is equation of linear charge density lambda dl. That is dl or dx. I have taken the length as x here. Therefore replace dl by dx. X square. This is a differential form of electric field at this point by infinitesimal value, differential calculus. What is the equation for a finite change? What is the equation for net electric field at this point by the entire charge accumulated here? That is, we get it by integration of the equation. Integration on the left hand side is this. Integration on the right hand side is this. This is constant. Remaining is integral of the function dx by x square with limits from a to a plus l. Why limits a to a plus l? The charge is commencing from this point, ending at this point. Therefore, from this point we will take where the point there is no charges here, space here. So the starting, that is lower limit, the charge commencing. Now the charge amount increases as the length increases from this side. That is why lower limit and upper limit. Minimum here, maximum here. Charge is minimum, maximum. That is from A to A plus L. That is a variation charge. Integrate this function with these limits, gets the total electric field at this point by this infinite number of charges. They are arranged in this linear fashion. That is why integration, integration of 1 over x square with dx is 1 minus x minus of 1 by x. Then the limits, apply the limits, upper limit, lower limit, we get like this. So write the positive value plus negative value like this is a mathematical equation. After the integration, we get this mathematical equation for a finite value, that is for a total effect. That gives electric field at this point. Electric field at this point by the linear charge density when the point is along the axis of the linear charge. That is what the mathematical expression. Let us go for this derivation, it requires this kind of geometrical drawing. Let me brief about this geometrical drawing. I have taken the point here. Draw a straight line perpendicular to this, passing through this point. A straight line like this. And the distance between this linear charge and the point is, let us call this as A. And on this linear charge, I am taking this element, infinitesimal element, that is dx length. It contains infinitesimal amount of charge dq. Infinitesimal amount of charge dq. So, what is the electric field produced by this point due to this infinitesimal charge? That is, draw a line, that is electric field line like this. That is the electric field dE at this point by this infinitesimal charge. That is a line drawn, a straight line drawn from this point to this point, and the distance between this point and this point is r. That is drives. And also distance between this point and this point where the line is drawn, it is x. Length is taken as x. And the total length is specified as L. Length of this linear charge. And let us call this the angle between these lines as theta. And also let us draw a line between this point, this end of the charge, and this point. Straight line, of course dotted line, and also one more straight line between this point and this point, this end of the line. That is straight line, dotted line. And let us call this angle as theta 1, this angle as theta 2. That is theta 2. It is, of course, it is in the clockwise direction. That is, if the line rotate like this, it is in the clockwise direction. That carries positive charge. This theta carries positive charge, positive sign. And this line, what is that, rotate in the opposite direction, anti-clockwise direction. Therefore, this theta will take negative sign, minus theta. Yeah, of course. Now at this point, the equation is, what is that? Equation is d is equal to, same equation, that is same kind of line, k into, what is that? K into d is equal to k into different infinitesimal value. Electric field at this point is infinitesimal value. It is equal to Coulomb's constant to amount. Coulomb's constant into amount of charge is dq at a distance of r. It is at a distance of r from this point is r square. Rewrite this in terms of, what is that, linear charge density lambda dx. Similar to the previous one. This is dE in terms of, what is that, linear charge, that is in terms of length parameters, dx and r. Then later, for a total effect, for a total change, you write the integration of this. If you integrate this with this function, the integration becomes a laborious and also it is a tedious. It becomes a laborious process with this. If you substitute this, all these things, and do the integration, this integration is easy, but this integration is, what is that, laborious, becomes tedious further. So let us simplify, what is that, in the simplified way of integration. Let us convert this, what is that, length into other function of theta. It is possible. That is total length into function of theta, theta 2 to theta 1. Total length is L. The total angle is theta 2, theta 1. In that way you can do that. So in terms of theta, what we get? In terms of theta, if you want to express, terms of theta function, then easy for integration. For that, let us take cos theta. That is, triangle is rectangle triangle. This is theta. If you write cos theta, what is cos theta? Cos theta is adjacent by hypotenuse r, a by r. That is, cos theta is equal to a by r. What is r? A by cos theta. If r equals a by cos theta, what is r square? A square by cos square theta. So that is r square. Look at this equation. The r squares, that is, r can be represented in terms of theta. R square as a square by cos square theta. That is in the form of theta. Length in the form of theta. It is represented, specified. Similarly, we specify the dx in terms of theta. For this, let us take tan theta. Tan theta of this triangle is opposite by adjacent. That is x by a. Opposite by a. So x is equal to a tan theta. I want dx. For this dx, differentiate this with respect to theta. What is dx by d theta? If you write differentiate this by respect to theta, differentiate this also with respect to theta. That is a secant square theta. The differentiation of tan theta is secant square theta. This equation related as dx is equal to a secant square theta into theta, a secant square theta into d theta. Look at that. Dx can we write it as a secant square theta d theta. It is in terms of theta. So substitute. This is called as equation 3. This is equation 2. This is equation 1. Put this equation 2 and 3 into equation 1. That is what we get. dE is equal to k lambda into this secant square theta d theta divided by a square cos square theta. Simplify. Cos square theta, that is a square by cos square, denominator goes to numerator. Secant square into cos square theta, cancel. Secant and cos are inversely related. And 1a is there, a square is there, 1a cancel. 1a remains in the denominator. The remaining is k lambda d theta by a. K lambda d theta by a equation. So this equation reduced to this equation. That is what you have done. You have transformed, that is, change the function of x into theta, the function of length into theta. We get this equation. This is the equation. So this is a vector. The magnitude of this vector at this point is this. But this vector, let us know, you have to resolve this vector into two different components. That is horizontal component and vertical component. Because net electric field is the vector sum of these two components. That is why we take this vector, we have to resolve into a vector of two different components, horizontal component and vertical component. It is x, it is y. Let us write this horizontal component as x and vertical component as y. So rewrite this. What is that? This is the one. It is d, that is ex, ey. Y represent horizontal component. X represent y represent vertical component. X represent horizontal component. d cos theta, d sin theta. Horizontal component, vertical component, horizontal component. You have to simplify this. Substitute for d, substitute for d, take them together simultaneously. What is d? D is this. That is dx dy. It is d sin theta, d theta. D theta is there is a differential expression or differential equation, differential function for this point. I want what is the finite or total effect, total electric field. What is Ex component for finite changes? That I told you, it is integration of the function. Integration of the function. These are constant coming out of the integral sign. So only the function is theta. So integration of this function and the integration of this function. What is the limit we apply? That is very important. Correct limit. Correct limit is, it is theta. I told you this theta 2, this is what is negative value. It is minus theta 2 plus theta 1. Minus theta 2 to plus theta 1. That is the correct limit. Minus theta 2 minus theta 1. Minus 2 plus. Then do the integration of the function. As you know, integration of cos theta is sin theta, and the integration of sin theta is minus cos theta. Limits, these are the limits. Apply the limits and simplify. That is sin theta 1 minus of sin theta 2. And you know that sin of minus theta, sin of minus theta is minus sin theta. That is why minus of minus becomes plus for second term. It is plus sin theta. So sin theta 1 plus sin theta 2 with limits. What is the limits when you apply? That is cos theta 2 minus cos theta 1. Here cos of theta, when you substitute now cos of minus theta minus 2 minus theta 2, we know cos of minus theta is cos theta only. Cos of minus theta is plus cos theta. Use that formula and apply. With limits, we get cos theta 2 minus cos theta 1. This is Ex, this is Ey. This is the component along X, this is the component along Y. That is a mathematical derivation, integral, what is that? Integral equation for a finite value at this point. The net the total electric field or the net total net effect is this plus this. So that is a general mathematical formula for the electric field at this point for a finite length of linear charge. For a finite length of linear charge. This is the one. So with this we can calculate or simply what is that, understand what are the different possibilities we come across with this equation. This is a mathematical equation, general mathematical equation for electric field for this linear charge of finite length. If this finite length is infinite linear charge, for a linear, that is infinite length, if it is infinite in length, there is one possibility. If charge, linear charge is infinite in length, infinite means it will extend to infinite value. If that is the case, the theta, what is that? The variation of theta, the angle, what is that? It is always like this, rotate like this. This theta 2, what is that? Rotate like this. For infinite length, this becomes pi by 2, that is almost a vertical direction. That becomes pi by 2. It means the case for the infinite linear charge, theta 1 equals theta 2 equals pi by 2. Both the angle approaches pi by 2. If that is the case, what would be the E net? E net is equal to electric field at the point is equal to, substitute for theta 1, theta 2. It is pi by 2, sin pi by 2. It is 1, sin pi by 2, 1 plus 1. Similarly, what is cos pi by 2? Cos pi by 2 is 0. And cos pi by 2 is 0. 0 minus 0 is 0. This becomes 0. And the first term remains what is 2k lambda by a. That is a mathematical expression. Simplify, almost it is simplified to that, very simple. 2k lambda by a. the net electric field at this point. Net electric field at this point, if the linear charge is infinite in length, that is one possibility. The other possibility is semi-infinite linear charge. What is semi-infinite? Finite means this side the length is extended to infinite, this side the length is extended to infinite. What is semi-infinite? Semi-infinite means this length only extended to infinite length. Only this side. This length compared to what is that? Almost approaches to zero. That is, this angle approaches to zero. This angle will approach to pi by 2, 90 degree, as the length is extended to infinite distance. Pi by 2. Only one angle is pi by 2. For this semi-infinite linear charge, what would be the electric field? Net electric field is again this plus this. Substitute for this theta 1 and theta 2. Theta 1 is pi by 2, theta 2 is 0. That is pi by 2 and 0. Sin 0 is 0, sin pi by 2 is 1. Similarly for theta 2 is 0. Here theta 1 is pi by 2. Look at theta 1 is pi by 2. That is cos pi by 2 is 0. Theta 2 is 0. Cos 0 is 1. So this is 1 unit. So overall what is that? This is 1, 2 k lambda by a. So this is a net electric field. If this length is extended to infinite, only this end, that is this side is extended to infinite length. But this side is extended to infinite length. What about the value? This value becomes 0. If you relate, what is that? Theta 1 is equal to 0 and theta 2 equals pi by 2. This comes to be 0 for this infinite extension of this length. You can check it later. What is that? So this is what for the semi-infinite linear charge electric field at this point. And final one, the other possibilities. So look at this. The other possibility is here theta 1 is equal to theta 2. When theta 1 equals theta 2, if you take this point as a midpoint of this linear charge, midpoint, exactly at the midpoint, this side length remains same, this side length also equal, that is equal length on either side. Then the angle, that is these two angles must be equal, that is theta 1 is equal to theta 2. We say some angle is pi. Substitute this into this equation and see what you get. So this is sin pi, sin pi. Sin pi means 2 sin pi. And this is cos pi minus cos pi means 0. Cos pi 0. That is 0. Cos of pi minus cos of pi 0, that is 0. That is, this term becomes 0. This is only 2 k lambda sin pi by a. That is a mathematical equation or mathematical definition for electric field at this point. When theta 1 is equal to theta 2, when you take the vertical point exactly at the midpoint of this linear charge. So these are the different possibilities. We can arrive at the equation like this using this equation. This is a general equation. That is a mathematical expression for E net at this point by this linear charge. So this is how we can derive the electric field at a point by this linear charge distribution. Thank you very much.